All right, everybody, hello and welcome back. Today what we're going to do is we are going to apply our transformations to specific functions. Particularly, we're going to talk about quadratics and we're going to talk about absolute value. So all of the rules that we've talked about in our last couple lessons, the last couple of videos, is all going to be applied to new situations, except now we're going to be able to figure out what our parent function f of x actually is. So those rules that we came up with are now going to be applied to specific equations. So here's kind of what I'm talking about. We have our first problem here, which is an absolute value function. Now we've got our new function, which is g of x, all right, that has some transformations in it. What we want to do is come up with our parent function so we can apply the transformations to get a new table to graph. Well, in order to do that, we need to know what a parent function is, and that is essentially when we have a function without any of our transformations. So if I just cross out, shade out our transformations, what I have left over is our parent function. So in this case, it is just the absolute value of x. So now I can fill in my table. I'm going to erase my crossouts here so we don't forget later on. And all I want to do is focus on f of x now. So what I'm going to do is I'm going to take each of these values and I'm going to plug them into that function. So I have the absolute value of -1, which is 1, the absolute value of 0, which is 0, and then the absolute value of 1, which is 1. So this is what my parent function is going to look like. If we want to, we could continue to do other values. The absolute value of -2 is 2, -3 is 3, and then we could do the positives as well. Essentially, that is going to leave us with a v-shaped function like this. So looking at that graph, we could fill out our domain and range. Now, our domain and range is going to be different than our previous activities because we're not just going off of the graph now. We are going off of this function, which means there are values in it, as we can tell by our arrows, that aren't actually included in the table. So we need to use our brains a little bit here and put together some information. If we think about our domain as how far to the left and the right we're going to go. Well, if we look at my left side, we're going up, but we are also moving to the left. So that means we're going to continue to approach the left side and keep going and going and going, which means we're going to approach negative infinity, which I want to put a parenthesis around because infinity, negative infinity, those aren't actual values we can get to. They're numbers that keep growing and growing and growing. So the same idea works to the right. We've got an arrow going up and to the right, but remember, domain is just about left and right. So we're moving further and further to the right, further and further along our positive x-axis, and it's going to keep going. So it's going to keep going all the way to infinity, and again, it gets a parenthesis. Now, our range is similar, except we're going to be focusing on the up and the down, right? Our y values, our outputs. So if we think about the lowest value that our function goes to, we've got that point right there. Well, that point has a y value of 0, but it's an actual point, so it gets a bracket instead of a parenthesis. In either direction, we have arrows that are going up and to the sides, but the key part that we care about now is the fact that it's going up. So it's going to keep going up and keep going up all the way towards positive infinity. So that is the domain and range of our parent function. That's what our graph is going to look like. What we need to do is identify our transformations. As we learned before, whenever we have multiplication in front of our function, it is going to be a vertical stretch. In this case, it is of 2. I've got a plus 2 at the end. That's going to be a vertical shift up 2. And I know that because outside, not directly attached to my x value, means vertical. Adding or subtracting means a shift. And so it's a vertical shift, and we're adding 2, so it is up 2. So what that means is I can take my vertical values from my parent function, and I can apply my stretch by multiplying by 2. And then I can apply my shift by adding 2. So I'll get 4, 2, 4. And now I apply my other transformation, which is actually directly attached to my input. So if I plug a number in, immediately to simplify, I have to subtract 3. That's what tells me that my 3 in here is a horizontal transformation. I'm adding or subtracting, so it is a shift. And although it says -3, typically we would think left 3. Remember that your horizontal transformations are kind of opposite of what they seem. So instead of -3, it's actually going to be +3, so it is right 3. So what I'm going to do is take my x values and add 3. So I get 2, 3, 4, and now I can plot my new function. So I've got 2, 4. I've got 3, 2. And then I've got 4, 4. So if we use the same shape as our parent function, which is a v, our function should look something like this. Now, if you think about it, look at the red graph and then look at our purple graph. It should look like we are stretching it vertically twice the amount, which is why it's a little bit steeper in here. But then we are also shifting it right 3 and up 2, which we should be able to tell is a pretty accurate representation based on what we have on our graph. So then the last thing I have to do is talk about my domain and range. Domain is always left to right. Again, I've got arrows on either side pointing out, so that means I'm going to continue in both directions. So I'm going to go all the way to the left, which is -infinity, and all the way to the right, which is +infinity. Now my range is my y values, so the lowest point is this one right there. That has a y value of 2, and again a bracket because that is an actual point. And then arrows pointing up, which means our function is going to continue to rise, continue to go up all the way towards +infinity. So this is an application of what we've been learning in our previous activities. It looks a little bit different because we can actually figure out what our parent function is going to be, but the application process is still the same. Everything that is directly attached to our input is going to be horizontal. Everything else is going to be vertical. Addition and subtraction are shifts, multiplication is going to be stretches, and negatives are reflections. All right, so it's important to keep in mind whenever we see these lines in here, that is the absolute value function. Essentially, that's just asking us how far away from 0 each of our values were, which makes sense, right? The absolute value of -1 is 1 away from 0. 0 is 0 away from 0, and 1 is 1. So this is an application of what we've been learning so far. Lastly, we're going to take a look at a different type of function. So again, we've got our g of x here, which is 2 times -x to the second power. Same idea as before. I need to come up with information that's going to go in my parent table. It's going to go in here. Now, we could really use whichever x values we want. Same thing up here. We could really use whatever we want. But the key idea is I want positives and I want negatives. We want to be able to see both the left and the right side of our graph, which is why I chose to use -1, 0, and 1. Now, what I need to do is I need to find my parent function so I could plug these values in to get matching points. In order to do that, we are going to cross out our transformations. Therefore, what I have left is my parent function, which is just x squared. So all I have to do is plug these numbers in. -1 squared is 1, 0 squared is 0, and 1 squared is 1. So if I plot those points, it looks very similar to what we had before, except now we're dealing with quadratics, which means they're going to curve up a little bit more. And here's what I mean. 2 squared is 4, so that would actually be another point there. And then -2 squared is also 4. So as you can see here, this curves a little bit more than our absolute value function. It is called a parabola. It is almost like a U shape. So that is what our quadratic is going to look like. We can go back and do our domain and range now, looking at the graph. As you can see, on either end, again, we have arrows going up, but they're also going out to the sides. That means they're going to continue going out to both sides forever. So our domain is going to be from -infinity to infinity. Now that range, we go from the lowest point, which is right there, that has a y value of 0. And again, a bracket because it's an actual point. And then we've got arrows pointing up, which means it's going to keep going all the way up to infinity. So if we didn't remember, domain is left to right. It's our inputs, our x values. And then range is like our y values. It's our outputs. All right. So I'm going to erase what I crossed out before. So now we can label our transformations. All we have to do is take those same rules we've learned in previous lessons and apply them to this table to get a new one, which we can then graph and get g of x. So every time we have a negative, this is going to be a reflection. We knew that before, the same thing still applies. Now the key part here is that negative is attached to my x, so it is a horizontal reflection. This 2 is on the outside, and again, it's not really about the parentheses. It's about the fact that it's not directly attached to x. If I were to plug something in, I would need to apply the negative and then square it, because it's a quadratic, that square is really important. Anything that happens after the squaring is going to be a vertical transformation, which is where this 2 comes into play. So it is vertical because it's not attached to my x. I am multiplying, so it is a stretch of, and in this case, our vertical transformations are exactly what they look like. So a vertical stretch of 2 is the last transformation. All I need to do is apply these. So the first thing, why don't we just do our reflection first? If I'm going to reflect something horizontally, it's going to flip from left to right. What that means is our negatives are going to become positives, and our positives are going to become negative, which we can see by multiplying by -1. So we get +1, 0, -1. So essentially our values just flip-flopped, all right? And we'll talk about why that is in a second. And now I can apply my vertical stretch, which is 2. So I'm going to multiply by 2 to get 2, 0, 2. So if I plot my points, I get -1, 1, 2, 0, 0, -1, 2. So it's going to look like this. Now, what's really happening is we are stretching it up, but we are also reflecting it horizontally. Quadratic functions are symmetric across our y-axis, which is why you can't really tell by the graph that we reflected horizontally. Now, absolute value functions are also symmetric across the y-axis, so it'd be difficult to tell there as well. But as you can see from our table, we did actually apply the transformation. It's just not as evident in the graph. The last thing I need to do is my domain and range. So if we look at that graph again, I'm going up in both directions, but I'm also moving out. It's not quite as far out as it seemed before, but we're going to continue to move our way out, which means nothing's going to stop us from doing so. I'm going to move all the way to the left and move all the way to the right, so our domain is -infinity to infinity. Our range, again, is the lowest point to the highest point. Well, our lowest point is down here that has a y value of 0. Because it's a real point, it needs to be included. And then we've got arrows pointing up, which means our y values are going to continue to grow all the way to infinity. Now, one thing you might have noticed is that the domain of absolute value and the domain of absolute value and domain of quadratics are always going to be -infinity to infinity. That's always how it works. And essentially the reason behind that is you can always plug in any x value you would like to a quadratic and absolute value function. There is no restrictions on what you could plug in. So this is kind of the gist of what we've covered over the last couple days. We are applying our transformations and the rules that we learned about negatives being reflections, multiplications being stretches, addition and subtraction being shifts to specific equations. Before, when we did this, we just applied transformations to generic equations like this. And again, the rules are still the same. Adding or subtracting is a shift. Multiplication is a stretch. Something that affects the input, so directly attached to my x, is horizontal. Something that is not is vertical. Same rules, different situations, because we now know what these functions look like. We know quadratics look like parabolas. They are parabolas. We know that absolute value functions are v's. All right, same rules as before, just getting a little bit more specific because we're talking about specific functions. As always, thank you for listening. If you have any questions or concerns, please feel free to reach out. Thanks.